Welcome to our video on the normal distribution, and at the end I'm going to show you how to compute a bunch of things, basically all of our descriptive statistics using the TI calculators and Excel. So if you already know how to do either one of those, by all means, don't watch that part. Okay, so our only objective really is to talk about z-scores and things like that with the normal distribution, and then we'll tack on some technology to the end of the video. Okay, so what exactly is the normal distribution? Well, everybody knows what the bell curve is, right? Everybody knows what a normal distribution looks like. What you don't realize is that all data in the known world will have a normal distribution if you sample from it over and over and over again, right? So if we talk about the distribution of data, it can have any distribution you want, right? So you can talk about a population of data. If you took it all of something, right, an entire set of data, it might have a bell curve. It might have a normal distribution, but it might not. It might have a uniform distribution, right? It looks like a rectangle, just a flat bar. Like if you looked at rolling a six-sided die, right? They each have an equal probability of 1/6. So that's going to be a perfect, what we call a uniform distribution. Or you might have something that is really skewed to the right or skewed to the left. You can have things that are bimodal, that have multiple peaks and valleys. All of these parental things, right? So we're talking about this is the shape of a parent population that's skewed right, right? You could have something that's bimodal, right? Or you've got more than one hump type of thing. It doesn't matter what shape your parent population is, right? So it doesn't matter what shape the huge population is. If you sample from that over and over and over again, right? So you take every possible sample of, let's say, size 40. So take a sample of size 40 from this and take every single possible sample of size 40. So there's going to be, millions and millions and millions, depending on how big your population is. And then you calculate a statistic from that sample. So let's say every single time you take a sample of 40, you calculate the mean. We're going to talk about the average. So you're going to take the average of each sample, and then you plot the values of those, right? You do like a dot graph where you put a dot for every time you get a sample with that amount. What's going to happen is the distribution of your samples is going to be perfectly normal. And the average of all of those samples, right? If you take the average of the averages, more or less, the average of those samples is going to perfectly match the average, what we call mu, of our population. And it doesn't matter what shape the population is. When you sample from it over and over and over again, that distribution of samples will always be normal. That's called the central limit theorem. That's something we're not going to talk about in this video, but it's one of the reasons why it's very important that you understand how the normal distribution works, because everything advanced in statistics is based on the idea of the central limit theorem. So everything builds on the idea of understanding what the normal distribution looks like. So what are its characteristics? It's bell-shaped, meaning it only has one mode. It has one peak, and that peak is right in the middle, and it's perfectly symmetrical. So if you were to fold that thing in half, it would match up perfectly. The mean, median, and mode are all the exact same thing. So again, if you were folded it in half, that middle value, right, that highest peak, the top of the curve, is both the mean, the median, and the mode. Okay, the total area under the curve is always equal to 1. So that's how we can start calculating probabilities, is because probabilities have to add up to 1. The area under the curve adds up to 1. So we can now calculate the probability of something happening based on the area between 2 points. And it's completely defined by its mean and standard deviation. So a normal distribution is defined by its mean and standard deviation, just means that that shape can be anywhere on a number line, right? It doesn't have to be centered at 0, which is what we call the standard normal curve. So the standard normal curve is centered right here in the middle of the number line, right? The average is right here at 0, and its standard deviation is equal to 1. But it doesn't have to be that. We could have a normal curve down here that has a much thinner standard deviation, right? So now maybe the standard deviation is equal to, let's say, a half, and its average is, let's say, -10. But that's still a normal distribution, right? It still satisfies parts A, B, and C. And D just tells us that we can locate this thing anywhere on the curve. Or we could have one that was really wide, right? It's not as tall, so it's wider, because remember the area has to equal 1. So if we make it taller, it's going to be thinner, and the thinner ones have a smaller standard deviation, and this one, maybe the standard deviation is 4, something like that. Okay, so it can be located anywhere, and it can have different standard deviations, and all that's going to mean is it's either wider if it has a large standard deviation, or narrower, thinner, right, if it has a small standard deviation. And it can be anywhere. It can have an average that's way up in big positive numbers, or it can have an average that's way down in big negative numbers, right? So it can be anywhere on the number line, and it doesn't matter. It still holds true with those first 3 parts. Now, a z-score is just a fancy way of describing where we land on the normal curve. And the reason why we do z-scores is we want to be able to standardize things. Let's say the blue curve represents one set of data and the red curve represents another set of data, and you pick a data point, right? So you pick one data point out of the red curve and it lands right here, and it has a value, and on the number line, let's say its value is -8. And then you pick a data value from this curve, and let's just say the average here was 100. So then you pick a data value here, right? And it's an X because it's on the number line. And that value, let's say, is 107. And you ask yourself, okay, well, which of those data values is further from the mean, right? Further above the mean? Well, according to just the raw numbers, this one is 2 numbers above, right? Because it went from -10 to -8. This one is 7 numbers above because it went from 100 to 7. But we're not asking, is it further away in actual numbers? We want to know if it's further away in relationship to the rest of the group. Is it more extreme than the others? How much area under the curve is in the tail, right? If we calculated this area in this tail and this area in this tail, which one is bigger or which one is smaller? Because if there's not a lot of area to the right, that means it's way up near the top, and it's got, a higher percentile. We've talked about percentiles in other videos. So z-scores are ways of describing that distance from the mean in relationship to the entire set of data, because the first thing you do is calculate the actual distance from the mean, right? You take your data value, you subtract the mean from it, and that tells you how far you are from the mean. So in the case of the red one, right, our distance would have been 2, right, because we're above it to the right, so it's a +2, and this would have been a distance of 7. Okay, great, but now what does that mean? Now we want to relate it to the standard deviation. So basically, how far are we from the mean in terms of standard deviation? So this one, we're a distance of 2 above it, but the standard deviation is 1/2. So doesn't that mean if we do 2 divided by 1/2, we actually get 4? We're 4 standard deviations above, right? Because every 1 point is 2 standard deviations, because you go 1/2 and 1/2, that gives me 1, and then 1/2 and 1/2, that gives me another 1. So if we're above it by 2 points, then we're above it by 4 standard deviations. Whereas over here, even though we were above it by 7, a standard deviation is 4 points. So this is less than 2 standard deviations above, right? It's 1 3/4. It's 1.75. This is less than 2 standard deviations above, whereas this one is 4 standard deviations above. So can you see that this one in red is more extreme? It's further away from the mean than the other one, even though it was closer in terms of raw distance, right? It was a distance of 2 and this is a distance of 7. And that's how we can standardize things, right? Z-scores is a way of standardizing things. So we can say that one thing is this many standard deviations away and the other thing is this many standard deviations away. So we can talk about it in similar units. It's kind of like if something is 12 inches away and something else is 25 centimeters away, how do we know which one is further away? Well, we can standardize it by converting them both to centimeters, type of thing. Well, since we can't really convert them both to numbers because they're already at numbers, we convert them both to standard deviations, and then we can compare those distances in terms of standard deviations. We've standardized the steps, right? We've standardized how far it takes to get one standard deviation away. Okay, so how do we calculate some simple z-scores? Well, it's very easy. We just use the formula data value minus mean divided by standard deviation. So we always need to know the mean, right? We need to know the standard deviation, and then we can calculate z-scores of anything. So it's just a matter of throwing those things into the formula, doing the math, negative 1.59 for the first. And so we can see that 148.2 centimeters is 1.59 standard deviations below the mean. Do the same thing with the next, and we get 0.11. That means that's 0.11 standard deviations above because it's a positive number, right? And then if we have things that are in different units, we have to convert them to the right unit. So this one was, kind of silly because 1.7 meters, we'd have to convert that to centimeters, which makes it 170, and that gives us 1.48, or about 1.5 standard deviations above the mean. So units matter. You don't see a lot of examples where the units are different because usually we're talking about scores, test scores and things like that. And so all the numbers are based on the same unit. But if you have something that's a measurement like inches and centimeters, well, those can obviously be changed, right? Because inches can go to feet and yards and miles and all those weird things, and then centimeters can go to meters and kilometers and all those other measurements. So anything like that, you do have to worry about changing it, but usually the numbers are just raw data that are kind of more of like a score or something where there's not really a measurement to it in the true sense of measuring a distance. Okay, so whether your mean is here at 159.5 or if your mean is down at negative 300, you can think about these distances being converted to standard deviations, right? How far does one standard deviation go? Well, instead of talking about it in point values, we can just say it's one standard deviation. Okay, all right, how about this? See if you can, should have been pretty easy, right? You're just plugging it into the formula and doing some simple math. Another example. Suppose that the average caloric intake for women is 2,050 calories per day with a standard deviation of 175. If we assume that caloric intake follows a normal distribution, find the percentage of females in your class that consume more than 2,000 calories per day. Now, we always have to assume it takes on a normal distribution, but remember I told you that even if caloric intake doesn't have a normal distribution. If we sample from that population, we know our collection of samples will in fact have a normal distribution. So we can still play this game because we know that we could play it on the samples, right? The distribution of samples. Now, the number one thing I tell my students whenever you're dealing with z-score questions, the first thing you always want to do is draw a simple basic picture and label what you have, right? So here's my mean. My mean is 2050, and they want to know the percentage that consume more than 2000. So we're basically looking for something that's pretty close to the mean, right? 2000 and above, right? Well, we know something about normal distributions. We know that the mean cuts it in half, and we know that the area equals 1. So don't we know that the area from the black line to the right is going to be exactly 0.5? And since this is a little bit to the left of it, don't we know that this answer should be a little bit bigger than 0.5? Yes, and that's a good thing because it helps us catch any mistakes, right? If we did this and we got this answer and then we looked this up in a table, because that's what you have to do with a z-score to actually get the probability, you could very easily get the wrong answer. Or if you have technology, you can let technology do it for you, but you can also still get the wrong answer if you type something into technology wrong. So it's always good to draw a picture and know basically what you should be getting. Now, if we use the TI calculator, we can do the normal CDF function and go from negative 0.29 up to, and then what this is 1e to, that's just the biggest number you could do. You could just do point and then just put in 9999, just put a bunch of nines. And that's kind of like the same thing as infinity, and it'll give you the area to the right of that. And you can see that the area is a little bit bigger than 50%, 61.41. That seems a lot bigger than 50%, right? So that 50 calories, went from 2050 down to 2,000, actually gave us an extra 11.4%. But at least we know the answer should have been a little bit bigger than 50. And this seems reasonable enough that we shouldn't think that we did anything wrong. All right, how about another? Now that we've learned how to do standard deviation, or sorry, now that we've learned how to do our z-scores, the next two examples are going to be how to do all of this stuff with calculators. So here's a set of data. Here's some more data. And we want to calculate standard deviation using the calculator. Well, it's really easy, right? We can follow this. Second data, choose one variable, press enter, press data, blah, 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 blah. You can read through these if you want. It might seem a little confusing just to read through them, which is why instead of reading through them, I'm going to show you how you can do it with an actual calculator. Okay, so bring up your calculator. If you want to calculate any of your what we call descriptive statistics, mean, median, mode, standard deviation, range, quartiles, Q1, Q3, all that kind of stuff, you can do it very easily from your calculator. The first thing you have to do is enter your data. So if you click Stat and choose Edit, this brings up your list, and you type these in one number at a time. I already typed these in one number. So you type in a number, hit Enter, type in a number, hit Enter. I already did this just to save some time. Okay, so once your stuff is in your list, you're good to go. The next thing you do is go Stat, Calculate. One variable statistics right there is exactly what you want. Hit enter, and now it's going to ask one variable statistics on what list. If your data is not in list 1, you can see down here that you've got lists in yellow letters above. So like if it was in list 4, you could do second 4 and it would calculate on list 4. But our stuff is in list 1, and list 1 is the default. So if you just hit enter, it uses list 1. Here's my mean. Now here's some stuff we don't need. This is the sum of all my x's. This is the sum of all my x's squared. These help us to do other calculations. This Sx is the standard deviation if we consider our numbers to be a sample. This is the standard deviation if we consider our numbers to be a population. We normally consider it to be a sample, so you're normally going to use that one. N equals 20 tells me there's 20 pieces of data in my sample. If I scroll down, I also get my minimum value, my Q1, my medium value, my Q3, and my maximum. It gives me everything but mode, right? So we can get everything but mode out of the TI-83 very easily. But that's fine because usually our data sets are small enough that we can get mode just from kind of looking at them. Okay, so that's how we do it with the calculator. Very, very simple. If you wanted to do that previous example with figuring out the probability, right, of this one, you don't even have to calculate a z-score because you can do down here there's vars for variables, and above it is distribution, distr. If you do second vars, it brings up your distribution menu, and you can see the first one is normal PDF and then normal CDF. I'll move this over here so we can see everything. Choose normal CDF. Now what you do is you type in where you want it to start. So it needs to start at 2000, comma, where you want it to end. All right. And then comma, the mean, and then comma, the standard deviation. And you have to calculate the z-score. What it does is it calculates it for you. If you had done just 2000, comma, all those 9s and hit enter, it would calculate it based on a standard normal of 0 and 1. So if you do calculate your z-scores and you want to do it with z-scores, you can do it with z-scores, and it's the same idea, right? So instead, if we go second distribution, all right, normal CDF, and put in the z-score. Now, if we double check what the z-score was for this, you'll recall that it's negative 0.29. So you got to do negative, right, 0.29, comma, and then again, go out to infinity, so just a bunch of 9s, and then hit enter. And you see how you get basically the same. The reason why it's not exactly the same is negative 0.29 is actually rounded, right? If we would have taken this out to more decimals, these two numbers would have got even closer and closer. But the best way to do it, right, the most accurate way is to just use the normal numbers. So the left number, comma, the right number, comma, mean, comma, standard deviation, and that gives you area under the normal curve for any situation. So let's say you had to do the area below 2000. So if you had to do the area below 2000, second distribution, normal CDF. Below 2000 means we have to go negative 99999999999, comma, you know what, this isn't going to work because that's the wrong negative. Sorry, I got to use, you can't use the negative from your key. You got to use this negative, and then 99999. So we're going to go as far left as we can up to 2000, comma, a mean of 2050, comma, standard deviation of 175, right? And we know that the area above it was 0.6124, so shouldn't the area below it be 0.3, 887, blah, blah, basically almost 0.39. So there it is, 0.387, blah, blah, blah. So that's how it works. You can do area in between any two things using the calculator very simply. Okay, how about doing this stuff in Excel? Well, there's the same idea for doing things in Excel as there is for doing it in your calculator. So some more data, right? They talk about what they want you to do with it. The first thing you have to do is this add in this analysis tool pack. Again, I don't want to mess going through all these slides. You can go through these slides on your own if you want to try it that way. I'm going to show you guys how to do it in real time. So here's my data. I want to calculate all of my descriptive statistics in Excel. But the first thing I have to do is go to File, Options, down here to Add-ins. And you can see these are inactive add-ins, but we want to manage our Excel add-ins, and we want to tick on Analysis Tool Pack because that adds in the Analysis Tool Pack. So usually when you install Excel, it doesn't add this in because it doesn't want to be too bloated unless you need it. But if you add it, it doesn't really take up that much extra. But you see it added this extra little kind of portion to the menu ribbon. If you click on Data Analysis now, it's going to bring up your menu that's going to allow you to do all sorts of cool stuff with your numbers. You can do ANOVAs, correlation, F-tests, T-tests, Z-tests, regression, all sorts of cool stuff. And if you just do descriptive statistics and hit OK, it now says on what data. So if you go over here and highlight your data, it puts it in there for you, right? And then if you had labels, like if this first thing just said data, then you could tick on that and it would know it was called, that first thing was data. But since we don't, we're good to go. And then you can tell it where to output the result. But just you can tick on these to play around with them. But I'm just going to have it open in a new worksheet. And there we have it. Double click on this so we can see everything. There's my mean, my standard deviation, median mode, standard error, standard deviation, variance, kurtosis, and skewness, things that we'll probably never see, but in case you need them. There's your range, your min, your max, your sum, your count, and then a confidence level. Again, that was just because I played around with it. You don't really need that. But you can see it gives you everything except for Q1 and Q3, right? It didn't give you the quartiles that we got out of our calculator, but those are really easy to do. And you can also do area under a normal curve with Excel, but it's not as easy. I would just say do it with the TI calculator, especially since you have emulators. Okay, so that's everything you guys need to know for this video.